Hello, everybody. Welcome to the new Headworks International Food and Beverage Live event. Today, we will have Vice President Afnan Din. We will have Chief Technologies Officer Dr. Sam Basu, and then we will have Siva Angappan joining us as well to speak. First, we will have Siva begin the presentation. Thank you everybody for joining, and make sure to leave any questions in the comments below, and we will answer them at the end of this presentation. Thank you.
Thank you, Matthew. My name is Siva. I'm the Director of Process Engineering at Headworks International. Good morning, good afternoon, or good evening, wherever you are around the world. So today we're going to have a LinkedIn live presentation of our technologies for food and beverage industries wastewater treatment. So the agenda for today is, first we'll talk about the challenges faced by the food and beverage industry. Then we're going to introduce some basics of the MBBR technology, our core technology. And then we will talk about a modification of our core technology in the anaerobic MBBR. And then we'll go through case studies explaining our situation, our installations in greenfield as well as retrofits, turnkey solution and other things. So the challenges faced by food and beverage industry is multifold. So if you are running a food and beverage plant, you know that in North America they are charged a surcharge to discharge the wastewater to your local treatment plant. Those surcharges have been increasing in double-digit percentages every year. Over the last 10 years, it has doubled in terms of amount of money charged for discharging, as well as the loads discharged. In many cases, the food and beverage plant is in a city area, and there is no space to expand. So they have to find new additional space for expanding the plant. So we will our technology can expand the plant without new tanks and equipment. The other costs, like operating costs, are also very high now. The energy and water are more expensive now. Over the last 3 years during COVID time, many of the costs have increased by 50% due to inflation and other reasons. So we'll address each one of these challenges and how we can solve these challenges. So food and beverage industry is very diverse. There will be plants like a brewery, or it can be a soft drink, it can be a meat. So the BOD, COD, all those things are very highly variable. It can be as low as 1,000 milligrams per liter, or it can be more than 10,000, 20,000. In a distillery, for example, the BOD can be up to 20,000. Whereas in a small food packaging plant, it can be 1,000 milligrams per liter. Typically, for discharging to a local treatment plant, your limit will be 250 BOD in TSS. Whereas discharging to your surface water, it can be as low as 10 milligrams per liter. And the FOG in the wastewater can be highly variable as well. In a meat plant, you will have high FOG, fat, oil, and grease, or it can be non-existent in a soft drink plant. Similarly, TKN ammonia can be very high, 300, 400 milligrams per liter in a meat plant, whereas in a soft drink plant, it will be non-existent. So we can go through some of the case studies to show our installations in food and beverage industry. So the surcharges, the number one challenge faced by food and beverage industry. Typical limit to discharge to your municipal plant is 250 BOD in TSS, ammonia less than 45. These are typical municipal wastewater limits. So municipal plants don't want to deal with any wastewater stronger than municipal wastewater. So they make you treat this wastewater up to this level. So the surcharges are quite variable in the US. It can be as low as $1 for 1,000 gallons, or it can be as high as $2 for 1,000 gallons. This is very diverse in different locations. In California, Texas, water is scarce, so they charge a lot more. Whereas in southeastern state, it can be low. Similarly, California BOD surcharges can be very high, whereas in the southern states, it can be very low. So you can see the typical limits. These are the middle range. There are many states under this dollar surcharges or over these surcharges. This is just the middle part of the surcharge limits. So when you are looking at typical mid-size food and beverage plant, we took a case study of 250,000 gallons per day discharge based on the lowest surcharges, and then BOD 1,000 pounds per day, which is about 450 kilograms per day, and TSS ammonia, this kind of loads, how much surcharges will be charged. Typical plant like this size, they'll be paying $1,000 per day or $365,000 per year. As you see, this is a very large amount. We have installed some MBBR plants in food and beverage plants where the payback of the surcharge is about as low as 1 or 2 years. That means if you spend $500,000, you can recover the surcharges within a year and a half. So that there's a short or immediate payback by installing a treatment system to avoid the surcharges. So the operating cost is another challenge. Labor cost used to be $20-25 per hour just a few years ago. Now it's almost $50 per hour for technical labor. So the MBBR, as we propose, has a minimal operator attention. I will explain in case studies later on. Whereas the energy costs also have increased by up to 50%. So those kind of situations, you may want to consider anaerobic technology, anaerobic MBBR. Our version is called EnergyCell. And our anaerobic technology can not only save energy cost up to 80%, but it will also generate energy in terms of biogases that can be used for heating. So it can be a net neutral or positive in terms of energy consumption. And if we don't have any space to expand, we can offer multiple solutions. For one, we can do a small MBBR plant in a small location, or we can expand or using the existing infrastructure, such as tanks and other equipment on site. So with minimal space to expand, we can increase treatment capacity in terms of flow or in terms of meeting new requirements or increased loads. So MBBR basics, I'm going to briefly touch on this. So typical biological treatment systems can be divided two broad groups: suspended growth, such as activated sludge, or attached growth, such as fixed film systems. Within suspended growth, you have MBRs, SBRs, and other technologies. So SBR is a batch technology, whereas a conventional activated sludge is a continuous flow technology. In attached growth, it can be a rotating biological contactor, RBCs, or a trickling filter. Trickling filter is a static fixed film, so the media itself does not move, whereas dynamic fixed film, like an RBC, the media itself is moving around. MBBR is a variation of the dynamic fixed film technology. In an RBC, the media is contained in a large drum, and then the drum itself rotates, which is prone to failure in terms of bearings and other things. Whereas MBBR, it's a small pieces of media floating in a tank and mixed in a tank. So there are no moving mechanical parts in an MBBR. So everything inside the MBBR is basically maintenance-free for over 30 years. There's no failure or anything like that in an MBBR process. So there's a newer version of the MBBR technology called IFAS. The only difference in an IFAS compared to MBBR is that we recycle the sludge. So this is advantageous when you have an existing activated sludge system and you want to expand capacity in terms of flow and loading. We can use this IFAS technology to expand the capacity. By recycling the sludge, you bring in the activated sludge, and you also have media in the tanks. So that makes it a combination of fixed film as well as suspended growth technologies. The footprint of this technology is even smaller than MBBR because you have two different processes running within the same tank. The only difference is that in MBBR, we tend to use DAFs, which has a small footprint, and IFAS technology will try to use the existing clarifiers. So why would you choose one versus other? MBBR, you will choose if you have a greenfield site, and if you don't want any kind of operator attention within the biological reactor. So many of our MBBR plants don't have a dedicated operator. The production plant personnel come to the wastewater plant once in a shift and check everything and go back to production. So that's a big advantage when you have a high labor cost, and especially for small wastewater plants. In an IFAS technology, you will probably need a dedicated operator monitoring MLSS and RAS, all those things. It's suitable for larger plants or for retrofitting an existing plant. We can use IFAS technology for phosphorus removal, biological phosphorus removal, and we can also use it for total nitrogen removal as well. In an MBBR process, generally used for BOD only removal processes. And if we have a large meat plant, for example, we can use the IFAS plant to remove total nitrogen as well as phosphorus. So biological nutrient removal can be done with the IFAS process, a combination of fixed film and suspended growth processes. MBBR is more generally used for pre-treatment, industrial pre-treatment, to meet pre-treatment standards to discharge to a municipal plant. And it can also be used to retrofit lagoons or trickling filters, RBCs, those kind of things, or replace them. There are some case studies, we'll talk about it later on. So the advantages of MBBR, I want to go through it, summarize it. So it's a single pass technology. What that means is that there is no recycle or MLSS to maintain. So water goes in, water comes out. The biomass is retained on the media. It has compact footprint, so only 1/4 of the space required for activated sludge. So if you have an activated sludge plant already, we can actually expand the capacity 3 times, 4 times flow capacity, or in terms of loading using the existing tanks. We don't have to build a new tank. So that's a big advantage if you have a plant and you want to expand and we don't have any new space, we can retrofit the MBBR process into that plant. It's robust, so it can handle large loads and variation. As you see on the right, you see a biofilm picture with a single piece of media. And that piece of media shows that the biofilm, within that small opening, the biofilm can expand and shrink depending on the load. It's automatically done by the bacteria, so you don't have to maintain any kind of conditions other than pH and DO, monitor them. So there's a built-in buffer capacity within the MBBR to handle large flow and load variations. And the second one is the HRT, hydraulic retention time, is not a limitation for the MBBR technology. The reason is that our design is based on surface area loading rate, the amount of media in the tank, not based on retention time. So you can have a very small tank with a lot of media, so that flow that can handle as much as 4 times the active sludge. Go back to the previous slide, please. Yeah, I want to finish off this. So the toxic loads, if you have a toxic chemical coming, for example, you have cleaning chemicals in the food and beverage plant, like chlorine or quaternary ammonia, the MBBR biofilm can handle this much better than activated sludge. Since the bacteria is floating in an activated sludge plant, it's vulnerable to the toxic chemicals, whereas the biofilm itself is hundreds of layers of thick. When you have a toxic chemical going through the biological system in a biofilm, only the top layers die off, and the bottom layers are strongly attached to the media, and then they grow back. So there is no washout of biomass like an activated sludge system. MBBR, it's very difficult to wash the biomass of the media. It can be done in a modular fashion. So if we have a plan to build out the production in over a number of years, you want to start with 25% of the capacity, then you will start with a small amount of media in the tank, and then we can keep expanding as needed. So there are, many plants we have started with 25%, and we have gone up to 75% media fill. So that's built-in capacity of almost 3 times. So you can start with 1/3 of the capacity and build out the plant over time. So you don't have to spend all the money upfront. And within the biofilm, you have a buffer capacity to handle the large flow and load variations in a short time frame. That concludes the part of the MBBR basics. The next part will be the anaerobic MBBR. Dr. Somnath Basu will take over here.
Hello, good morning, everyone. I'll be very brief. So anaerobic treatment, and there are again two types of commonly used treatment processes, and accordingly, there are the different types of reactors, and anaerobic MBBR falls under the category of moving bed biofilm reactors. Here, the movement is conducted by mechanical mixing, because the reactions take place under anaerobic condition without aeration. And this slide shows the biochemical reaction steps. There are 4 steps, 4 basic steps: hydrolysis, acidogenesis, acetogenesis, and methanogenesis, conducted in series by different types of anaerobic microorganisms. So the process was developed first in the laboratory of University of Manitoba, and then it was scaled up to a pilot scale, and then at a brewery in Manitoba. So now the process is well established, and the first commercial installation has been in 2023. Headworks also has a patent on this technology, and I'll go through some basics. So basically, the mature biofilm was developed within 2 months, and this is as opposed to a longer startup process with suspended growth anaerobic processes, and 80 to 90% COD removal was achieved. Then the OLR, organic loading rate, we achieved about 23 kgs per cubic meters per day and 37 liters per day of biogas production. I think I will skip this slide. This has some comparison of our pilot scale data versus whatever has been reported in the literature, and they are very comparable. In certain cases, they exceed what has been reported in the literature. Okay, so in essence, what is an anaerobic MBBR? It is anaerobic process combined with MBBR technology, and so basically it derives the benefits of both biofilm processes, fixed film processes, and anaerobic processes, and it is applicable for high strength liquid waste, typically greater than 3,000 milligrams per liter. Then the biomass grows on the media support as biofilm, and because there is no aeration, mixing is provided by mechanical mixers. The pH has to be monitored, because if there is not sufficient alkalinity, it consumes alkalinity. Anaerobic reactions consume alkalinity. So there may be a trend to reduce the pH, and so that has to be monitored, and if necessary, pH has to be added, alkalinity has to be added to maintain the pH in the optimum range. And nutrients, for the most part, may not be needed for food and beverage waste, because it comes with the wastewater. It is derived from the actual food, but if needed, there may be addition of phosphorus and nitrogen as needed. And then these reactions take place under anaerobic mesophilic condition, 30 to 35 C, and it may need downstream polishing. It depends upon the regulatory requirements of the downstream processes. Okay, so basically, as I said, it combines the advantages of both anaerobic processes and MBBR technology. The advantage of anaerobic process is elimination of aeration energy, which is about 50% of operating cost in a treatment system. And then because the sludge growth is very low, order of magnitude less than aerobic processes. So the sludge storage and hauling cost is minimized, and which is about 20 to 30% of the operating cost of any treatment system. And then biogas production as a fuel, which can be utilized for boiler or other purposes. And the benefits of the attached growth processes: low SRT, low reactor volume, low feed footprint, and hence less capital cost. And then because it is fixed film, so it is protected from washout under the shock loads and shock flows. So that is the summary. And then this is a typical MBBR reactor. You can see the gas and then the treatment system, the treatment reactor with mechanical aerators, and then the dosing systems. Okay, then we move on to the case study, and it is a case study for the first plant that we supplied to do a project, to a beverage project in Mexico. And I'm not going to go through all the details of the design, but the effluent is residual effluent is 536 BOD and residual BOD is 179. And this is because about 80 to 90% of the COD is reduced and the remaining part has to be aerobically treated. Okay, then we move on to some of the case studies, and I pass it on to Mr. Din, who is the Vice President of our Middle East region. Mr. Din, please.
Thank you, Dr. Som. So the first few case studies actually will be spoken about by Siva, and then I'll cover the case studies in my region. So Siva, just go ahead.
Thank you, Afnan. So the first four case studies are in North America, so I will be talking about that. So Hershey's Creamery is an ice cream plant in Harrisburg, Pennsylvania. So they had a situation where they were building a greenfield ice cream plant. But they said initial 1 or 2 years, they'll be running the plant at only 1 shift per day. And then later on, they will build out to 3 shifts per day, depending on the demand and production capacities. So for that, they needed a flexible treatment system that can be expanded in a modular way. So we proposed a 2-tank system with the low media fill. So we will design the overall system for the future capacity at 15 GPM at very high loads. But initially, we will design for 10 GPM at low loads and build it over time. So the BOD and COD are very high. They had a preference to aerobic MBBR technology because they didn't want any kind of operator attention to the plant on a sustained regular basis. They wanted somebody to go check the wastewater plant once per day. So due to these constraints, and also since it's a greenfield site, we proposed aerobic MBBR preceded and followed by DAF. So the BOD is 7,500, which is pretty high, and they have to meet less than 200 to discharge to your local municipal plant without having to pay surcharges. So if you meet the 200 and 200 and the TSS, they don't have to pay any surcharges to the municipal plant. So it requires 2-stage systems because you're going from 7,500 to 200. So that's more than 98% removal of BOD. So we proposed a 2-stage, 2-train system. And the ammonia is consumed as a nutrient by the bacteria, so you don't have to remove the ammonia here. And similarly, FOG is removed by the pre-DAF, so you don't have to worry about in the MBBR plant. And phosphate are already lower, so you don't have to remove that. So this plant has already started up. It's running right now only 1 shift per day. When they are ready to expand, they will add more media without building any new tanks. So that will it will be a modular system. So this is a poultry plant in North Carolina for House of Rayford. They had an existing activated sludge system, but around 2018, they had their chicken demand doubled over the year of 2018. But they did not have space to build a new activated sludge system, so they were looking at asking us for some ideas. So we proposed what's called a roughing reactor, which is placed up front, shown in that picture. The plant itself is very high flow, 1.5 mgd, and they didn't have to convert it to add a new activated sludge system. They would have required 200 by 200 feet large size plot to add the activated sludge system. What we proposed was a roughing reactor in front of the activated sludge system, shown in the picture there. That's about 40 feet diameter. Within that 40 feet diameter, we are able to remove about 90% of the BOD. So the activated sludge system following the roughing reactor MBBR can handle the remaining BOD as well as the nitrogen removal, ammonia removal. All right, next slide, please. This is a potato chip plant for Frito-Lay in Peru. They also make corn chips here. So they had an existing trickling filter which was failing, but they did not have any space to put a new system to replace the trickling filter, because they wanted to use the trickling filter area for some other production storage area. So we put in a very compact 8 feet by 30 feet long MBBR plant is shown in the picture. It's basically on a walkway in a plant area. So that's all the space they had available. So we put in this very compact MBBR plant handling 400,000 gallons per day of flow and removing 70% of the BOD from 1,000 to 300 area, 300 milligrams per liter of BOD. This is again a roughing reactor. The effluent from this plant is discharged to activated sludge and then discharged to the city plant. So this is a fishery packaging plant. So they take fish from another plant and then cut it into pieces and process it and make frozen fish products in Danvers, Massachusetts. So they had an existing trickling filter plant, which was very smelly and nuisance for the neighbors, which was so they needed a new technology to replace the trickling filters. So we put in a complete turnkey type system. We provided the DAFs, pre-DAF and post-DAF, as well as 2-stage MBBR reactor to replace the trickling filter. So it handles 70,000 gallons per day, BOD 1,500 milligrams per liter, and is discharged to the sewer without paying any surcharges. By doing the MBBR technology, they have awarded surcharges as well as handle municipal complaints about smell and noise, other issues. And those are the 4 case studies in North America. Afnan will talk about the next case slides.
Excellent, thank you, Siva. So I'll be going through some case studies from different wastewater in the food and beverage industry. The first one is Tanmia Poultry Plant. So this was a poultry plant in Saudi Arabia where we supplied a complete turnkey solution. It was an existing activated sludge plant where the flows and loads had increased because they had increased the slaughtering of chickens. So they had more load to treat. So what we did, we offered a retrofit solution of an existing activated sludge plant where we increased capacity and improved effluent quality so they could reuse it for irrigation purposes. Our scope in terms of what we supplied, we did the complete plant design. We supplied all the electrical, mechanical equipment. This includes equalization tanks, aeration grids, blowers, the design of the activated sludge plant, coupled with the retrofit MBBR solution, both primary and secondary DAFs, as well as sludge dewatering. And we did the installation and commissioning. So the only thing that Headworks did not do here was the civil works. Apart from that, we provided everything. So the system was designed for 1,200 cubic meters per day. Typically in poultry effluent treatment, You have high TKN. So you can see here that we had very high TKN, 350 milligram per liter. We had to achieve an effluent of less than 5 milligram per liter. COD is high, around 5,000, but it's highly biodegradable waste. The BOD was around 2,750, and we had to achieve less than 40 BOD in the outlet and less than 125 milligram per liter COD in the outlet. Here you see the proposed scheme and the scheme that we followed. After the influent, there was a pre-treatment screenings system we supplied, followed by equalization. After the equalization, we have primary treatment through a primary DAF. In the primary DAF, we dose polymers to primarily remove solids and associated BOD. Then we had an existing activated sludge tank, which we retrofitted with a MBBR roughing reactor to handle the additional loads that were coming in. And we kept the existing activated sludge plant as a activated sludge reactor and used the existing surface aerators. So the MBBR reactor was retrofitted as part of that CAS reactor. You need some pH correction upstream of the biological step. So that was provided, followed by a secondary DAF to remove the solids generated from the biological step. The sludge was then treated, both a primary sludge from the DAF as well as a secondary sludge from the secondary DAF was then treated in a belt filter press, and the final effluent was used for irrigation. So here are some photos. You can sort of see the installation. This is an equalization tank with aeration grids to ensure a homogenized influent to the process. The DAFs are provided in stainless steel. We use rectangular DAFs. They take up less space, and primarily that was the reason. This is the existing activated sludge basin with surface aerators. So we use the existing tank. So there was minimal civil works here actually, because the DAFs were provided as prefabricated, delivered to site, and all you need was a concrete slab. So they were sort of skid mounted DAFs. Just some more photos of the DAFs alongside the chemical dosing system, the scraper mechanism on the DAF, and just in operation. So this plant's been running now for about 8 years, and we were able to 100% reuse the final TSE, the effluent for irrigation. So we achieved the limits, and the plant is now producing effluent which no longer needs to be tankered or discharged. This case study is a milk factory. So this is a milk factory in Africa, where we provided a MBBR solution, an IFAS solution. It's a hybrid solution. It's an IFAS solution, which combines attached growth on the media along with activated sludge. Here, one of the big challenges here was the high COD. So you have very high COD, and the COD to BOD ratio is more than 3:1. And we were able to treat the effluent with a very compact, small footprint solution down to less than 30 milligram per liter BOD and less than 100 TSS. So the advantage of this proposed solution was that space was limited at site at the milk factory. They had very limited space. So they were looking for a solution which was very compact, as well as be able to work under low flow conditions, because initially when the factory was being set up, they were not anticipating to have enough flow and load coming into the works for the first couple of years. So an IFAS system provides that flexibility where you could run the plant at slightly lower flows, and as well as when it ramps up to full flow. So this is a two-stage reactor, two-stage process where you have two IFAS tanks in series. The first IFAS tank does the bulk BOD removal, and the second IFAS tank does BOD polishing. The solids are then settled in a secondary clarifier, and the RAS is returned to maintain a mixed liquor concentration in an IFAS tank. Here you see the two tanks in series, so it's glass line steel tanks, and these are the two IFAS tanks. So the carriers that we use to grow biofilm, we have a range of carriers, all with different surface area, ranging from around 400 meters squared per cubic meter to approximately 800 meters squared per cubic meter. So depending on the loads the capacity, what we're trying to achieve in terms of removal. We will select the ideal media to use, the ideal surface area. The fact that we have such a range allows us to customize our solutions for different types of wastewater. As you can see with these two examples already, that it's very strong wastewater in terms of load, very high COD, very high BOD, but COD to BOD ratios are very different. The poultry had a very high TKN, whereas this project here for dairy had very high COD coming in. And this is a project with Unilever in South Africa. This is an ice cream factory. And this has similar challenges to the earlier one, where its footprint was a big driver. They were looking for a solution which was very compact and took up less space. So this proposed solution here and what we implemented was primary DAF, followed by a two-stage MBBR, and followed by a secondary DAF. The COD was reasonably high at 8,200 milligram per litre. The BOD is as low as 4,100, and the design flow was 220 cubic meters per day. And we're able to achieve a BOD of less than 10 milligram per litre in the outlet, and COD of less than 50, and TSS less than 5. The final effluent here passes through UF and RO. So it goes through MBBR, secondary DAF, UF and RO, and then is fully 100% recycled. So here you see a very compact DAF. It's all sort of pre-assembled, prefabricated when delivered to site. So it's sort of plug and play. You see the MBBR tanks on the top left, and on the right, you see the carriers, which is this carrier is ActiveCell 920. 920 is the total surface area, but the biofilm grows on the internal surface area, which we refer to as protected surface area. So the surface area of AC 920 is 680 meters squared per cubic meter. And what you see here is how the biofilm attaches to the carrier. And this, in essence, is the reason why you have very small footprint solutions when using MBBR or IFAS, because we use a process where we use carriers to grow biofilm, and the carriers provide large surface area for biofilm to grow in a very small footprint. One thing to sort of notice here is also that the biofilm thickness is self-regulated. It's controlled through the aeration and the mixing in the tank and the collisions between the carriers. And that controls the biofilm growth. So that maintains a certain biofilm thickness, prevents the media from ever clogging, and it self-regulates based on the influent loads. So if the loads vary, which sometimes they do in different industries, depending on what's happening upstream in the production cycle, the MBBR process self-regulates. So it's very robust in terms of handling those variations in loads incoming. This is a project in Egypt. This is with Aroma Foods. It was edible oil. It was an edible oil plant. And again, you know, nearly all these references I've shared so far has very high COD. It's very high COD, has high BOD, and we're consistently achieving less than 10, less than 50 solids, less than 10 BOD, less than 100 milligram per litre COD. So this was edible oil in Egypt. So the proposed solution here was, again, we went with primary DAFs. We went with circular primary DAFs, followed by a two-stage IFAS process, followed by secondary clarifier. So we had a primary DAF to remove the fats, oil, the grease in the influent, and then we went with a two-stage IFAS, followed by a secondary clarifier. The photo on the left shows you during startup when we've added the media and there's no aeration. And without aeration, the media floats to the surface because the density of the carriers is less than 1. So they're very light, which allows them to easily mix. And on the right, you see when the plant's in operation and the media is mixing with the aeration on. So just to sort of summarize and conclude our webinar for today. In summary, you know, Headworks has over 25 years experience in MBBR IFAS technology. We're sort of one of the leaders in the market when it comes to biofilm processes. Our first commercial installation was in the last century. It was in 1999, so a long time ago now. And we have over 100 MBBR industrial installations around the world treating difficult to treat wastewater. So not just food and beverage, but we've done oil and gas, refinery wastewater, we've done petrochem, we've done all sorts of pulp and papers, mining, lots of different types of wastewater. We provide customized solutions. So we're really process experts. We can analyze wastewater characteristics and provide the solution that is best fit. We're very flexible in terms of what we supply. We can do turnkey solutions. We can do core technology. We like to provide process guarantees. We carry the process risk. We're not just a component supplier, but really knowledgeable in terms of doing process design. We do a lot of turnkey solutions for our industrial customers. We can also get involved at very early stages of a project in terms of when permitting needs to be applied for, planning permission needs to be applied for, when concepts are being developed. So it's not that we get involved at a very late stage on a project, but we can get involved and sort of work with end users and industrial customers to sort of look at when projects are being conceptualized. We also do a lot of pilot systems. We understand and recognize that pilot systems are an important part of validating our technology. We have ready-made pilots. We have ready-built pilots available. We send pilots to different sites to do a lot of testing. If clients want us to demonstrate the technology. And most importantly, we have a global supply chain. So, I mean, we're truly an international company. We manufacture our technology and we supply equipment from all over the world. We have facilities in North America, Europe, and Asia. And I think this is important part in what helps us deliver projects in all these different countries. So, yeah, that sort of brings us to the end of today's webinar. I thank everybody for joining on behalf of Headworks and our process team. And if there's any questions, please feel free to drop them in the comments box. Okay, so we've got a really good question from Bill. Thank you, Bill. Bill has asked, how many full-scale anaerobic MBBR installations do you currently have? And do you have an anaerobic MBBR pilot units available? Do you want to take that, Siva?
Yeah, so we do have an installation in Mexico for FEMSA Coca-Cola, and we can develop a pilot scale system. So that will be highly customized for each plant. So we will have to build a pilot for anaerobic MBBR technology for each site.
So we do have pilots. We just have to customize that for it to be an anaerobic MBBR pilot.
Correct.
So it certainly can be done, Bill. And maybe after this call, Siva will get in touch with Bill to perhaps discuss that further. Well, I don't think we have any questions, Matt. So maybe if you want to wrap up.
Yes, of course. That was Headworks' Food and Beverage live event presentation. I would like to thank everybody for joining, and then I would also like to thank our Vice President of the Middle Eastern, Afnan Din. I would like to thank Chief Technologies Officer, Dr. Somnath Basu, and I would also like to thank Director of Process Engineering and Technology, Siva, for joining us today. And I hope everybody has a great day, and thank you, and we will see you next time.